All right, in today's lesson for AP Calculus, we're going to be talking about algebraic properties of limits, and you'll notice that this entire first page of our notes is just listing a bunch of properties that we will see play out in different practice over the next day or two. And so if you're looking, there's a lot going on, but a lot of this stuff really makes sense. And especially as you begin to look at, like number 4 with the sum or difference rule, number 5 with the product rule, the quotient rule, you see that if I have the limit of two functions being added together, I can rewrite that in a way that allows me to take the limit of the first function, take the limit of the second function, and add them together. Same thing if I'm subtracting two functions, or if I'm multiplying two functions together like I see here. If I'm taking the limit of two functions that I'm multiplying together, I can take the limit of the first function, I can take the limit of the second function, find those two values, and then multiply them together afterwards. And so for the most part, like once we do practice, I think these things are going to make a lot of sense. The biggest one that I think might be a little bit different and a little bit like just takes some getting used to is this rule number 8 when we have composite, like we're taking the limit of composite functions. And we'll do some examples so that you see like why it is different to me and why it stands out as like, hey, this is one we need to pay attention to a few extra details for. Now, when we're doing this holds true for every single limit. And right now we're just going to like practice playing these things out. We've talked about evaluating limits from graphs. We've talked about evaluating limits from tables. Eventually, very soon, we're going to talk about evaluating limits algebraically when we just have the function. And a lot of these rules are going to play in more so when we're doing that. But we want to make sure we are feeling sharp with these rules before then. So that's why we're doing this lesson today. So might as well get right into it. Now, just to make sure we are straight on, we have two functions in each of these, f and g, and we see the graph of f on top, the graph of g on the bottom. When I'm looking at example A, I see that I'm taking the limit as x approaches 3 from the right of f of x plus g of x. The first thing I want to do, even before I look at the graphs at all, is rewrite my limit in a way that is easier for me to work with. That notation that we were talking about on the first page of our notes with all of this, with all of these properties, right? We want to actually write that down on our paper, and this is a step that AP will give you points for. They expect to see this step before you do any evaluating, and I'm sure some of us could do it in our heads, but they want, and therefore I want, to see this notation written out on your paper. I want to see it written out for every single problem because it's really important. Notation is going to be huge for us in AP Calculus, and it starts here. And you know what? We actually talked about a little notation thing on day 1 of AP Calculus saying, hey, right now we have the limit as x approaches 3 from the right of f of x. Does it still count if we don't have that f of x there, if we just have the limit as x approaches 3 from the right? No, it does not. That is not good enough. We call that a naked limit. AP will stop looking at your work if they see a naked limit. They will not even consider the rest of what you have. Naked limits are a no-go, and that is a notation deal. And so this isn't the first time we've seen this. Notation matters. Notation matters. I want to see this step for every single problem. All right, and so now we see that, hey, I can look at the graph of f and find the limit as x approaches 3 from the right. So at 3, as we approach from the right, looks like we're at a y value of 6. So 6 plus. And then we're going to look at g and look at the same x value, looking at 3 from the right. So here's 3. Looks like we're approaching a y value of 8. Excellent. And this is something we can obviously evaluate and come up with a final answer of 14. And we are good to go. Again, I want to say it one more time. Actually, this is not going to be the last time. So I'm going to say it many more times. Notation, notation, notation. I will go crazy if I don't see notation. It is so, so important. So might as well get used to it now. Notation matters. I want to see it. If I'm looking at letter B, I see I'm taking the limit as x approaches 5 of two functions that are being subtracted from each other. And I also notice that each of these functions has some sort of coefficient out front. And that is a property that is also on our front sheet. When we see that there's some coefficient being multiplied out front of our function, we can actually just pop that out front and ignore it until the very end. That is something that, again, is going to allow us to isolate our limit and keep it as simple as possible. And then we'll deal with some of that extra stuff at the end. And so when I'm looking at letter B, I'm going to rewrite this as 3 times, popping that coefficient out front, the limit as x approaches 5 of f of x minus 2 times the limit as x approaches 5 of g of x. All right, so when we are going to our graph, I'm going to look at 5, and this is a two-sided limit, which means I need to pay attention to both directions, what's happening as I approach from the left, what's happening as I approach from the right, and they need to be the same according to the limit existence theorem in order for this two-sided limit to exist. And so if I look at 5, looks like yes, from the left and from the right, we are approaching the same y value of 2. I'm going to do the same thing for g, a two-sided limit at 5. I care about what's happening at both sides, from the left and from the right. Again, it looks like we are approaching the same y value. And again, this is something we can evaluate. 3 times 2 is 6, minus 2 times 4 is 8. That's going to give us -2. All right, I think that you guys are ready to try C and D on your own, and so that's what I want you to do. I'll give you the time to do that, and then I want you to tell me what you get, and then we can check our work together. All right, so if we check C and D, I want to give us a little bit of feedback and tell you like exactly what I would be looking for. And so you'll see my first step for both C and D was my splitting of my limit, rewriting it with proper notation. That is something I need to see. If you didn't do that in your notes and you don't have that on your paper, I would not like your work so far. I need to see that notation. And from there, of course, we can look at the graph. Like for C, if I'm looking at the limit as x approaches -5 from the left, -5 is right in here. From the left, we just care about what's up here. It's a +3, which I see, +3. Then I'm going to go and do the same thing on my graph of G at -5 from the left. Looks like we're at a y value of 4. And 3 minus 4, I get my answer of -1. For letter D, I think it might have been just slightly trickier, but obviously still very doable. Of course, that 3, that coefficient that is with my f, I can throw that out front and just focus on the limit as x approaches -7 of f of x. And then divide all that by the limit as x approaches -7 of g of x. Look at my graphs, find that limit on f is 5, the limit on g is 3, and once I finally finish simplifying, canceling, I get my final answer as 5. All right, fantastic. Let's go ahead and do a couple more, apply a few more of the properties. For looking at letter E, it looks, innocent enough as we begin. So when I'm focused on rewriting it, I have 4 times the limit as x approaches 3 of f of x times the limit as x approaches 3 of g of x. And so when I go to my graph, let's see, go to F and look at 3. Again, this is a two-sided limit, so I'm focused on the left and coming from the right, and it looks like I have a value of 6. So 4 times 6 times, I'm going to go to G and look at x approaches 3. So something I notice about my graph of G, again, this is still a two-sided limit, which means I care about what's happening from the left and from the right. And something I see is that my one-sided limits are not equal to each other, which, of course, according to the limit existence theorem, means that our two-sided limit as x approaches 3 does not exist. And so when I'm looking at my work here, I can't multiply something by does not exist, right? That's not a number. That's not a thing. It's like we can't do anything with that. And so if any part of our problem does not exist, like that's going to be our final answer. So for letter E, that limit that they're asking me for, it does not exist because that one piece of our puzzle does not exist. All right, I'm not going to do all of these necessarily. I just want to focus on really two more to finish off strong here before we do that composition problem, that type, applying that property that I promised we would. I want to focus on F and G when we have something like to a power, to an exponent, as well as a radical. And something that's really nice about these properties is just like we were splitting for addition, subtraction, multiplication, division, it all looked the same. My property with exponents and with radicals is actually going to be really similar to my property with coefficients. Something we see here is that if we have, we're taking the limit of a function that is to some exponent, we can kind of do what we did with the coefficient and throw it on the outside. We can find the limit first and then take whatever number we get for that limit and take that to the power. Same thing with my radical. I can wait till the end, find my limit first, and then apply that radical. And so that's exactly what I'm going to do. Of course, we need to see our proper notation. That matters very much to us. And so I will have the limit as x approaches -3 of f of x. And I will take that entire value and I will square it. So I go to f and look at -3. Pretty sure we might have already done this. Looks like we're at -6 for that two-sided limit. And so once I find that value, I take -6 squared, and I get positive 36 for my answer. We will do the same thing for g. I have the limit as x approaches 4 of g of x. Going to have a coefficient of 8. I'm going to be able to throw that out front. And then I will take the square root of this entire thing. And so we will go to our graph of g, see what's happening at x as we approach 4. Looks like we're here. That's going to be a y value of 5. So I'll plug that in. 8 times 5. I multiply those things together and I get the square root of 40. Now, your Math 1 and Math 2 and Algebra 2 teachers would be freaking out right now about the fact that I just boxed this answer, the square root of 40. They'd be like, oh my goodness, you need to simplify this. You need to break it down so you have a final answer of 2 times the square root of 10. One of the most fantastic and beautiful things about AP Calculus is that as long as your answer is numerically correct, you do not have to simplify it. I can leave my answer like this, and I will get full credit. I do not have to do any extra work by simplifying, as long as it's numerically correct. And so I'm going to leave my answer just like that, and I recommend that you do the same. Yay, AP Calculus. I want to go ahead and move on to that last property, that property with compositions of functions. So we're taking the limit of composite functions, and that's what we see in example K. So if I'm not going to go through H and J with you. If you want to do those, I went ahead and put like a little bit of the work. The final answer for H will be does not exist. The final answer for J will be 0. And I highly recommend you do those for extra practice. But let's go ahead and focus on K. And so if we go back to our initial sheet that has all of our limit properties, and I'm looking at my composite function rule, it says that if I'm taking the limit of composite functions, meaning I'm plugging one function into another, I will take the limit of the inside function, which in this case is g, and then I will plug that number into my outer function. I will plug that into f in this case. So when I go back to letter K, I am taking the limit of the inner function, which in this case is still g, and then I will plug that value into f. And so when I go to g and I look at -2, which is here, That puts us at a y value of -3. And so I am taking f of -3. And this is what's going to make this property specifically different from the others, in that now we're not dealing with limits anymore. I am not trying to find the limit as x approaches -3 on the graph of f. I am trying to find the function value now. Where is my graph of f defined at -3? And so when I go up to my graph of f, and this is what can be tricky, and I'm looking at, what was it, -3, right? Yeah, -3. And I come down here. My function's defined at for an x value of -3 at a y value of -6. Now this just so happens to be equal to the limit as x approaches -3 of f of x. But that's not always going to be the case. And so I want to really make that point clear. We first evaluated the limit for the inner function. Now, my second step, I am focused on the function value. Where is my function defined at x equals -3? It's at a y value of -6. And that's what I want us to really practice for the rest of this time. And so we're going to do just a couple more together, and then we will be finished. And so if I move on to the next page and looking at letter A, I decided to start it for us to save a little bit of time. I'm taking the limit of my inner function, which is g, and then I'm going to plug that into my outer function, which is f. And so if I go to the graph of g and I'm looking at an x value of 3, it looks like my y value is going to be a +1. And that is the number that I'm plugging into f. I'm looking for, hey, on the graph of f, at +1, where's my function defined? And it looks like that is at a y value of -2. All right, we have 3 more examples. I want to give you time to try and take a shot at each of these 3. C is a little bit difficult, and so as you're trying it, if you run into problems, try to persevere, try to persist. Those are very, very important qualities of AP Calculus students. You will come across problems all the time that you have not seen before, and you're going to feel stuck at first. But I promise you, you're going to be able to do it. And I want to see that start to develop here with letter C. All right, we'll check in a second. All right, as you're looking at B and D, you can see some of my work. Something that you probably noticed when you were trying to evaluate B is that when you were evaluating the limit as x approaches -1 of f, you got your value down here at -6. And when you're looking at your graph of g to find g of -6, well, -6 wasn't on the graph. And folks, this is what I'm talking about being persistent problem solvers and perseverant problem solvers. Just because it's not there doesn't mean you can't find it. And so you'll see here, something I noticed was hey, I know this part of my graph is a line. I can kind of continue and extend my graph to find that the y value at -6 is going to be -7. And that's exactly one thing that you could have done. That would be great, right? Because this extends, this keeps on going. Another thing you could have done if you didn't feel like extending the graph in that way is write an equation for this part of my graph, right? I know how to write the equation of a line. And so let's call this part just like h of x. The slope is +2 going up 2 over 1. And then I just need to know what my y-intercept is. And so obviously if I know my slope and I go up 2 over 1 more, looks like my y-intercept is a +5. Well, I can plug -6 into this, and it will tell me what my y value should be. -12 plus 5 equals -7. Boom, I got the same answer multiple ways. AP Calc students can get the same answer multiple ways. It's one of the beautiful things about math. There is not just one path. And so do what you need to do what's best for you. But I certainly hope we didn't give up when we realized, hey, -6 isn't on the graph. I guess I'm just not going to do it. You can do it. I guarantee you. All right. I did want to talk about C to finish us off here. And so when we're rewriting this, right, f of the limit as x approaches 1 of my inner function, which is g, you probably got this far. And notice what I'm about to notice. When I look at the graph of g, as x approaches 1, right, that's a two-sided limit from the left and from the right. those are not equal to each other. And so you might have been tempted to say, hey, my one-sided limits they're not the same, which means my two-sided limit doesn't exist. So I'm going to say, oop, this limit does not exist. This is what makes limits of composite functions more difficult, is because you can't take that does not exist pathway and just stop your work there, right? We were able to do that earlier when we were multiplying functions and taking the limits of those. We were taking the limit of functions that were being added together, like in letter H. We were able to do that. Down here, we need to think about it in the way that, what is this actually asking from me? If it's asking the limit as x approaches 1, that's just saying, hey, do my left and right side limits, like, are they the same? And that's some of the work I need to do to extend this problem for me. I need to say, hey, is f of the limit as x approaches 1 from the left of g of x, is that equal to the f of the limit as x approaches 1 from the right of g of x? And if so, then that answer is going to be the response for our overall limit that they have asked us to evaluate. If those two numbers are different, then they're different. We can say it does not exist. Like we've been thorough. We've done what we can. And so let's go ahead and try it. The limit as x approaches 1 from the left on g. I'll erase some of this so I can see. As I approach 1 from the left, looks like I'm at a y value of -1. So I have f of -1. And when I look at f of -1, that's going to put me down here at -6. Okay, nice. So we have our first limit. I'm really hoping that the second one is also going to be -6. Let's see. The limit as x approaches 1 from the right on g gives us a y value of -3. So I'm looking for f of -3. That is a function value now. So at -3, where is my function f defined? Look at that. It is also defined at -6, which means because these two are the same, the limit they asked us for, the limit as x approaches 1 of f of g of x, is -6. So it does not exist. We do have a numerical answer for this limit. All right, that is it for our lesson today. One last thing I want to remind you of is, some of these properties, and specifically the property with composite functions, they can be a little bit tricky, right? This last problem we did, letter C, that took a little bit of thought and a little bit of thinking and perseverance. And so I want to remind you again that you have Khan Academy at your fingertips. And so if you are still feeling a little iffy, a little rough about what we just went over, you have resources in Khan Academy to go to. If I'm looking at today's lesson, determining limits using, limit properties, I have some different videos I can watch over limits of combined functions, properties. We didn't talk much about the piecewise functions one, but otherwise we talked about the rest. And they have these different practices, of course, too, which I will have you practice during class with me. So that's going to come. And I will say, you might get a couple of difficult ones, like some of those last few we did. But otherwise, a lot of them are going to be pretty straightforward, right? Like that first composition, limit of a composite function that we did, letter K, that was not bad. That was not bad. We were able to find that limit of the inside function and then evaluate it in the second function, and we were okay. Most of the problems are going to be like that, and so I don't want to, freak you out and make you nervous about going to practice, because that's the extreme example. But you know how to do them now. So I'll see you guys in class.